Well, it looks like it's official. We can get going. Welcome back, everyone. So we've made it to the last day of class. Congratulations. And today we're going to attempt to do the impossible and review 15 weeks worth of content in one day. We'll do the best we can going through those questions right here. And for what's coming up next, everyone should have gotten an email about contacting the right testing center. Coming down below here, don't forget to take a look at these documents as you're reviewing. And I'll still have office hours today, office hours on Thursday, and I'll be very available for email over Friday through Monday and into next week. So if you're working on WebAssign, working on old quizzes to improve your score, anything like that, please don't hesitate to reach out. I'll be very happy to help out. As far as the due dates go, there's a final due date for the course of December 9th. So that'll be the last day to work in WebAssign. It'll be the last day to turn in any quizzes that went overdue. And really, that's probably the first thing you ought to do for studying for the final exam. Work on those two portions of the course, and you're double tasking, really. You're improving your grade through homework and quiz grades and studying the course at the same exact time. Well, any questions about the final exam or otherwise, folks, before we begin the review? Okay, well, all the documents down here is really just for your self-study. And like we mentioned, here's the new document that we're going to go through. These problems are posted here. They're up on the top under blank lecture notes as well if you want to download a copy. And once we're done with these, we'll upload the solutions just as before. So here's how it starts. It looks like it's a 6-page document going down to the last official question that you could expect to see on the final exam. So starting at the very top, we'll go down the list here. And at any point, if you'd like to see a different problem solved, maybe from another sample exam, old exams, problems out of homework, those kinds of things, please don't hesitate to interject. There's no reason why we can't do a problem and then get sidetracked and do some other problem. There's no trouble there. But let's begin on example 1. Looks like we're dealing with continuity and something about a derivative. Really what example 1 is about is just a reminder that in calculus, pretty much every single thing that's interesting comes from a limit some way, somehow. So first, for continuity, it says express the function f is continuous at x equals 2. Express this information in the form of a limit. Really, all you have to write down here is this. Limit as x goes to. First thing we should take a look at is just choosing a color here, 2. Continuity at 2 means the limit is heading towards 2 for x. We have to bring in the function as well. So we go f of x, and from this portion, the actual continuity, it would look like this. If you're really continuous at 2, then we should be able to write f at 2. So this is the idea of direct substitution, essentially. Any questions, folks, with that first limit? Okay, that took us to section 2.5, really, with continuity. And now for this one right here, I think this is the trickier one. We have to be really careful where it says f prime. They're talking about a derivative in this case. So just from this portion right here, it says we need to write out the following. Take the limit as h goes to 0. The thing we take the limit of is the difference quotient. It goes f of x plus h minus f of x divided by h. And now from this part, because it really is an equation, we have to really write equals -2. So the equation above here saying that the derivative of f at 5 is -2 means this whole limit right here will exist and it will evaluate to -2 exactly. We'll look into this limit a little bit more on some of the problems down lower in this document. But that's one problem down so far. There could be a problem like either one of these on the real final exam, and I think this one made it onto exam 2, part A. Any questions, folks, before we take a look at the next?
I have a question.
Yeah.
Would we be plugging 5 in to the x plus h and f of x, or do we just leave it how it is?
Oh, that's a good call on that one. That would have been a mistake on my part. So if this was a real exam question and I was grading it, I probably would have gone -2 on that thing. Good eye on that one. If it says the derivative of f at 5, then right here and right here, we actually have to plug in the value of 5. So to correct our mistake, we can't do that on a real final exam, but just to emphasize, that should have been a 5 here and here. Thanks for spotting that, Jamie. Does that make a lot more sense?
Yes, it does.
Awesome. Other questions or comments with that one? Okay, glad we got that correction, and thanks again for spotting that one. So now, next examples, looks like we're just evaluating limits. Eli asks, would that be the final answer right there? Yeah, right at this format right here, this would be the end answer. Putting in an X here and here means we would have had to take another step and actually put in the value of 5. Other questions so far? Okay, well, let's give the problems down below a try. Looking at these limits, these are pretty tricky because sometimes they're really fast, other times they could be a long algebraic process. But what you're looking for primarily on some of these problems is continuity. If your function is continuous at the value you're interested in, then all you have to do is take your value and plug it into the function. Doesn't work on part A because if you plug in 0 for x, you divide by 0. This whole thing is a rational function. In other words, is not continuous at 0. We have to do a good amount of work. Well, not too much, but some algebra to get through that one. Well, if we look at this one here, the function is continuous at x equals 1. In other words, you can plug 1 inside e to the x squared minus x and get a real number out. That tells us we have continuity here. And so for part B, this one's immediate. You would just get e to the power 1 squared minus 1. So now it's e power 0 coming into just a 1. This is all due to continuity on this one. But here, we can't use direct substitution. We just have to expand out the numerator and hope things cancel just right so that we can take the limit. So let's give part A a try. Watch out for this on the real exam. There will be one where we're dealing with continuity, and this is literally all you have to do. But for part A, let's begin by expanding out that numerator right here. We have limit as x goes to 0. 4 plus x squared expanded becomes 16 plus 8x plus x squared. Once you FOIL that, you'll get two middle terms, 4x and 4x again, so 8x altogether. Subtract 16, divide by x, and here's our next step. 16s cancel. For the brave, you can cancel x right here at this step. I think what we typically did in class was this additional step. Take the limit as x goes to 0. Instead of canceling here where it's easy to make an algebraic mistake, you can factor out x, leaving 8 minus x. Still divide by x, but now this time, those two x's are gone. We have a brand new function, 8 minus x. That's a linear function. It's continuous for all real numbers x, which means all we now need to do is take 0, plug it in right there. So this idea in part A really gets used pretty much every single time you do a limit, but sometimes you'd have to take some algebraic steps until your function becomes continuous, like over here. So last step, plug in 0 for x, and you get a limit of just 8. So that's 2 limits down. There's got to be trickier ones down below, but any questions at the moment? Okay, this one down below here on part C is one of those limits where if you know a good amount of information about rational functions, which this is, then you might be able to just answer this question immediately. So let's give this two kind of responses. We're going to take a shortcut for the first one and then just do the full algebraic steps for our second response. Probably need more space on that actually. So let's call this method 1. Horizontal asymptotes. The idea about this is, if you're dealing with the limit as x goes to infinity, the only way this would exist is if the function, this one right here, has a horizontal asymptote. And it does. There's going to be, or does it? Hang on. The degree in the numerator is degree 5. We expand out the denominator, it would be u squared times 2u squared, so 2u power 4. That means the degree of the denominator is 1 less than the degree of the numerator. That means this one wouldn't have a horizontal asymptote. The limit would be equal to infinity. So that's my claim, just analyzing the function. That's kind of a weird way to answer an exam question, but if you answer just infinity on this one, I would assume you're thinking in terms of when the rational functions have horizontal asymptotes or not, and that would be an acceptable answer. But sometimes it's good to see this in a little bit more detail, so for the sake of the review, we'll do a second method. Method 2, I guess we could just call this algebra, where we're going to expand out the denominator and then go from there. Any questions before we launch into the second method? Okay, let's begin with it and go limit x goes to infinity. Denominator we're expanding where the red dot is, so u squared distributed in will give us 2u power 4 minus u squared plus, or excuse me, minus 4u squared plus 2. Numerator is 4u power 5 plus 5. I'll take an additional step just to combine like terms. Makes it easier to see what we're dealing with. The denominator, I must have drank a lot of coffee. My horizontal lines are a little bit shaky today. Let me try a little bit better on that one. That'll do. So denominator is 2u power 4 minus 5 u squared plus 2, 4u power 5 plus 5. And now the next thing we do with this method is we look down to the denominator. If we didn't notice that the degree is higher at degree 5 with 2 positive constants, giving us positive infinity, then we would just pick this out, divide all terms by u power 4. Let's scroll a little bit more. We would get a limit as x goes to infinity. Division by u power 4 here by the red dot will give us a 2 minus 5 over u squared when we divide here. And then finally on this one, plus 2 over u power 4. Coming up here, after division by u to the 4th power, we'll get 4u plus 5 over u to the 4th power. So now we're about ready to finish off the problem. Because x is going to infinity, anything with the denominator involving, hang on, let me take another look at this. Sorry, that must have been a weird formatting. If I'm using a variable u here, I'm kind of embarrassed how long it took me to notice. That should have been u heading towards infinity on each one of these. Let me see if I can just put in a quick correction here. So these all should have been u going to infinity here, here, and here on that last one. Eli says, why are we dividing by u power 4? Only because we're taking the variable u going off to infinity. So this is the major reason right here why in method 2, we divide by this. So if u goes to infinity, we have to go to the denominator and divide by the highest power of u, which in this problem came out to be u power 4. Now the reason to do that is when u is going to infinity and we divide by that highest power, we get to clean up all these things right here. This would converge to 0 because we have something getting larger and larger without bound in a denominator, divide by a finite number. Similarly down here, 5 over u squared would go to 0, and so would 2 over u power 4. And one way to think about any one of these is you could just do a really fast numerical experiment, even on a real final exam. You could go something like, let's analyze 2 over u power 4. It would be first 2 over, say, 2 to the 4th power. That's when u is 2. But u is going off to infinity, so eventually the denominator becomes 3 to the 4th power, 4 to the 4th power, 5 to the 4th power, and so on. But notice what's happening over here. As that base gets larger and larger, your values are getting smaller and smaller. So we say in the limit, these all converge to 0. So the long answer now finally made a little bit shorter is, if we want to know exactly what happens to this and not worry about eyeballing it and thinking about asymptotes, division by u power 4, the highest degree thing in the denominator, will cause all of these to converge to 0 immediately. And now the analysis on the limit is just based on 4u. The denominator is now positive, so as u goes off to infinity, 4 times u goes off to infinity like 4 times as fast now, then divide by 2, but the whole thing is now a limit of infinity overall. So the shortcut's nice, but these can be tricky functions, especially if you have to expand them. Method 2 just gets right down to the punchline. Well, any further questions, folks, with part C? Okay, sorry for the distraction with variable u on that thing. So far what's going on with these is when you see limits like these, if you're heading towards numbers that you can plug in a value, that's all you have to do and the problem is over. If you notice you're potentially dividing by 0, you might have to do some algebra first. But if the limit is going off to infinity, it's a whole different kind of limit. We're thinking of in horizontal asymptotes. And it looks like we have one more. X is heading towards -5 on this one. We would put a -5 here to get a 25. Here gives us -25, so we're dividing by 0. Looks like this one is another factoring kind of problem. So let's give this a try. Maybe let's not try to cram it in here. Let's put this on the next page. Sometimes when you're doing these kind of factoring problems, the denominator can be a pretty big hit. It's easier to factor, and once we factor out x from that, it could potentially help us see how to do the rest of the problem. Maybe. Let's see what we can get out of this. So first things first, we can take limit. X tends towards -5. And the denominator, factor out of x, and that will leave us at x plus 5. Because we have an x plus 5 here, we might have a hope of, when we factor this thing, x plus 5 could occur. Let's start factoring the numerator next. From the 2x squared, a natural thing to try is a 2x and an x. With a negative sign of 20, with a negative here rather, our signs have to be mixed. I'm going to try minus and plus, because now we're starting to match up the x plus 5 right here. Hopes of hopes is to cancel, so let's just throw a 5 here and just see if it works out. To get up to -20, we have to put a 4 here now. It's a good call to check this work, so here's the check. We want to multiply the outer. This will give us a 10x. The inner, this will give us a -4x. That sums to 6x, which is what we're trying to hit. That tells us we did factor it correctly. And because we're happy with the factorization now, x plus 5 has been eliminated. We can now cleanly cancel that off. And now it's a limit as x tends towards -5 of 2x minus 4 divide by x. This new function is continuous, so we just use direct substitution again. Plug -5 everywhere x occurs, and we've got 2 by -5 minus 4. Division by -5, so -14 -5ths, or 14/5 after simplifying. But we got it, folks. That's the value of this limit here. So a lot of these sometimes just involve some clever factoring. But if there's going to be a factoring coming up, like on the final exam, something like this is something that's a good thought. Work with the easier one and see if you can match up the next harder factoring. Well, any last questions, folks, on part D? Okay, so example 3 is probably not people's favorite question. Sorry about this one. We're going to calculate the derivative by using the definition of the derivative. There'll be only one problem like this on the final exam, and it has to say those instructions there. If those instructions are missing, do the derivative in the normal way. Just use the power rule 3 different times. We'd be expecting a 4x minus 3. But this problem is more about knowing the definition of the derivative, so we have to go through those motions. So first step, we can write out f prime of x equals. That's a really good call, even though you wouldn't lose points for not writing it down. It just reminds you what you're doing in the first place. We're calculating ordinary f prime of x. The definition is limit as h goes to 0, f at x plus h minus f of x divided by h. And this time we do leave the x as it is. Since we don't have a value we're calculating the derivative at, we want the derivative for all of the x's. This is a good time to kind of split up the problem. Let's work on f at x plus h, negative f of x separately, and then we'll plug in the results. Some people like to do it just all in one line. I'm kind of a fan of that myself, but if it helps to split it up like we're about to do, very good strategy then for the real final exam. So this is our f of x. That means f of x plus h is the result of going to something squared minus 3 times something plus 9. This function evaluation is essentially the same strategy that we used if we're doing, say, like a chain rule problem. We set up all the placeholders where things go and then just dump them in. So the placeholders are opened up anywhere x was. We dump in x plus h here and here, and then just start foiling these things out. So first it's twice. When you FOIL out x plus h squared, you'll get an x squared plus 2hx plus h squared. That's minus 3x plus h plus 9. Probably no cancellations all in this thing, but let's carefully get the rest of the terms. Distribute 2 in, and we have 2x squared plus 4hx plus 2h squared. Another distribution over here to give negative 3x minus 3h plus 9. So all that in blue would go right here. And this one's not as big of a deal, but if we're being really careful, and it's no harm in actually calculating that as well. Negative f of x just means we come up here and negate all the terms. So negative 2x squared plus 3x minus 9. So those are all the components. We just come back to the main problem over here and substitute in their values. So now at this stage, the derivative is limit as h goes to 0, 2x squared plus 4xh, or hx, however we decide to write it, plus 2h squared, minus 3x, minus 3h plus 9. Then now for this portion, just directly copy in these values, minus 2x squared, plus 3x, minus 9. I never seem to make those division bars long enough for these problems. Well, any questions, folks, to this stage, getting to that point? Okay, well, this is the fun part. Now we start to cancel everything. 2x squared, here and here eliminates. I don't think we have anything for 4hx, anything for 2h squared, but we have a cancellation at negative 3x and with a positive negative 9. So just 3 terms are left over. Every one of those terms has a factor of h, as it should, or else we would have made some kind of algebraic mistake at some stage. So since h occurs in every one of those terms, we can just factor it out and write limit as h goes to 0, h leaving behind 4x plus 2h minus 3. So I went through all 3 of these terms and just factored out the h. It's being divided by h, so these cancel next. as h goes to 0, 2h goes to 0. And that tells us the limit is now 4x minus 3 altogether. So we did it, folks. It's kind of silly to do this again because we know with the differentiation formulas, the derivative of this f of x is just 4x minus 3. But it's more about just knowing what the derivative is fundamentally as a limit and then running through it. I'm not going to ask a huge algebraic problem on this because really the major credit is knowing to write that down and getting to this step, knowing how to do the function evaluations. That's pretty much most of the credit for this kind of problem. Well, any questions, folks, before we go to another? Okay, I'm looking at example 4, and I think this may not be the best kind of problem for us. Let me see if I can fix this one here. Let's put a strike through on this one. This one can be done, but this one requires a different idea called implicit differentiation, which we didn't cover in this section. Notice that there's a y squared there. Let's fix this and make it a y equals rather than a y squared. Let's make it be a y equals x squared plus 3x minus 3. So just a small change in the function. We'll still plug in a 1, but if I plug in a 1 on this, we'll get a 1 plus 3 minus 3. Wow, that's lucky. It actually still has the right 0.11, but this is the more typical real function that you could expect on an actual final exam. Sorry for that one. I should have proofread that one a little bit better. So with that small change in, here's the methods if you're ever facing a tangent line problem. I would say a good step one is just calculate the derivative. So come over here to the brand new function we manufactured after noticing the problem, compute dy dx, or y prime if you prefer. We'll get a 2x plus 3. Even though it's a tangent line problem, we did not use the definition of the derivative because it wasn't indicated in this instruction at all. So do the fast process, the ordinary differentiation formulas. Once you have the derivative in step 2, what we're computing is the slope m. M is going to be equal to dy dx evaluated at x equals the first coordinate 1. So what this whole thing right here is trying to express, the Leibniz notation and the valuation bar, is go back to 2x plus 3, plug a 1 inside that result. So we have 2 by 1 plus 3. That information tells us that the slope of this thing is going to be a 5 altogether. Any last questions, folks, before we go to the step 3 to finish off this one? Okay, so here's our next step 3. We use the formula of y minus y1 is slope m times x minus x1. The y1 is also 1 on this one, but let's use color coding to indicate which is which. We'll go y minus 1, coming from the second coordinate, equals the slope m, which we computed as a 5, times x minus 1, the first coordinate. So we're just about there. We now have y minus 1 is 5x minus 5. So altogether, finally, the equation of the tangent line would be y equals 5x minus 4. So that's how pretty much any tangent line problem is going to come up. And it could be any function, really. It could be a simple polynomial, something with a square root. It could be a logarithmic expression. No matter what function you're looking at, same exact steps apply in the same order. Well, any questions at all before we try, looks like, exponential growth? Okay, let's give this one a try next. We should be hitting a section with derivatives. Yeah, that's example 6. Looks like the order here is not necessarily the order we did the class, but that's okay. So starting on this one, It says a bacterial culture grows at a constant relative growth rate. Just from this information right here, we can put down in part A, population size at time t is equal to initial population, p at 0, times e to the power k, that's going to be the growth rate, t. It says find an expression for the number of bacteria at t hours. And this is the expression, but we need to find next the initial population size, p at 0, and the growth rate, k. They tell us a couple pieces of information. Bacterial count was 500 initially. Because it said initially right there, what they're now saying is p of 0 is 500. So we can come back over to this equation and update our model. Population size at time t, sensing I need a little bit more space on this one, is 500 bacteria times e to the power kt. So next, if we can solve for k, the whole problem, well, part A of this whole problem would be complete. So we get to k by observing this information. This is a second condition that at 4 hours into this experiment, we have 39,000 of that bacteria. So we can take this and rewrite population size at time 4 hours is 39,000. But the moment we are putting down p of 4 on paper, we can go down to this expression. This is the population size at any time t, even 4. We'll be plugging 4 right where this t, oh, hang on, I'm not too sure what I even did there. Let's hope Control Z can fix that. Okay, sorry, got distracted. We're going to plug this 4 here in for t. So next step, we have 500 e to the power k times 4. Let me use a little bit of yellow just to signify what we did here on that step. It's set equal to 39,000. And this is the step where I remind the class, don't forget your calculator on the real final exam. Will be needed for steps like where we're at right here, and in a couple other problems we'll see. So first thing I need is just 39,000 divided by 500. Looks like that's an even 78. Wouldn't have guessed that. So e to the power 4k is 78. Let me double check that. Okay. Once we get to this stage, we're solving an equation with an exponential in it. So we use the opposite thing, a logarithm, and write down natural log e to the 4k equals natural log 78. We get a cancellation through the inverse functions right here, leaving behind 4k is natural log 78. And then last step, divide by 4, and k is natural log 78 fourths. That plugs in way up here, so the end answer to this is population size at time t is 500. E to the power, I'll put in t first, and then the value for k. Natural log 78 divided by 4. Well, this is the end answer on part A. Let me box it out just to express that that's what we were gunning for. For the next parts, we're just going to be working with this model to address these follow-up questions. But any questions or comments at the moment? Okay. Part 3 just asks for number of cells in 2 hours. If you have a calculator that you're using at the final exam with you right now, this is a good chance to practice along with the class. Let me know if you're getting something different, and we can try to diagnose and get it calculated just right. So in 2 hours, they're asking then P at 2. Population size at 2 hours just means plug 2 right here for T. So it's 500 e to the power of 2, natural log 78, divide by 4. And if you put this down on paper, even if you did make a mistake on the final exam and you got the wrong number, even if it's totally wrong, I would still give almost all the partial credit to this. Looks like I put here, this was a 3-point problem. So that means even if you get this wrong on your calculator, I'd probably give 2.5 points out of the 3. But it doesn't feel great to get nickel and dimed on points, so let's try to get this in carefully. So first step, let's just try to type this in verbatim. 500 e to the power 2 natural log 78. Make sure that your expressions you're typing in stays up in the exponent position. Sometimes that's the easiest way to make a mistake here. Then divide by 4. It looks like they all stayed up in the exponent, so that's pretty encouraging. And we get an answer of 4,415 to the nearest cell. That's rounding up to 4,416. Well, does that look about right to folks so far? Okay. Well, one thing you might do on this problem further is, if you feel like this number is not even in the right ballpark, maybe it's way too small, or maybe it's way too big, you could take another quick look at the model that you put in right here and just test it out. We plugged in 2 hours right here for t and got 4,416, but we're also told if we had plugged in 4 hours, we should have gotten 39,000. Let's check that out. Put a 4 right here, and yeah, it did come out to exactly 39,000. That gives us a lot of confidence that this number here is right. Let me delete it, put a 2 back in, and that's the number after rounding to the nearest cell. Now that takes us down to part C. This is the actual calculus in the problem finally. Find the growth rate. It's a major reason we went through all this stuff, just to see what the calculus looks like for a type of problem like this one. And this one involves a formula. It goes, the rate of change of the population with respect to time is equal to the growth rate of that population times the population size at time t. So that's the formula we're going to use, and looks like I'm going to be playing the game of trying to avoid the sun. Let me see if I can just change the angle here. Maybe. Okay, so we have that as our equation. So that means if we're doing this at 2 hours, we would rewrite it as dp dt at time t equals 2 hours. Oh, didn't mean to scribble on that. That was supposed to be a highlighter. So this now will come out to K times population size at 2 hours. So that goes in right there. But because we're doing population size at 2 hours, we're just using that number once again, 4,416. So this is now natural log 78/4 multiplied by 4,416. So we can go back to the calculator. Here's 4,416 pretty much. So you could just take this expression and multiply it by k again. But if you want to use this value down below here, here's what it would look like. I'm going to kind of lean back to avoid the sun. Natural log 78/4 times 4,416. So that tells us the growth rate at time 2 hours is 4,809.8. In terms of up here, the unit would have been cells because of the population size. Per, I'll just express as a fraction. Here we have time expressed in hours. So at the time 2 hours into the experiment, it's growing at about 5,000 cells per hour. If we redid this whole thing at, say, 2.5 hours, this would be much bigger. At, say, 4 hours, even bigger still. Well, any questions at all, folks, with getting through the exponential growth problem? I'm going to try the strategy of standing up now. Or maybe I can just move it up here and have the monitor block it. No, that'd be silly to try to work like that. Okay, give me one moment. I just lost the cable. I'm going to try to remember in the future to not select this particular room in a fall semester. It looks like this is a really bad one. Okay, well, it looks like we're now on to, I found a pen. Example 6, doing just ordinary differentiation. A lot of these differentiation problems we have to do sometimes do come up with a little bit of setup. So say, for example, on this problem right here, I wouldn't want to differentiate it right as it stands, because by the red dot, that would be a quotient rule, for example, or you're using the power rule in a pretty tricky way. So first step on this one is just rewrite f of x as -3 x power 4. Oh, sorry, I forgot we're rewriting it. Let me try again. What I need to do is bring x as a base up into the numerator. So I should have wrote -3 x power -4. Now we're on the right track. Everything else looks like it's just fine for differentiation, so I'm copying from this point on. Plus 9 natural log x minus 5 to the power of x plus natural log 6. Now we're ready to go. The derivative is really fast to calculate. I'll do the first term. When we're differentiating, -4 will multiply the -3, so we have a positive 12. New power of x is 1 less, so -5. How about a volunteer for the class on this one? Anyone see what would happen when we differentiate natural log x?
Would it be 9? Or like would the ln just turn into a 1, so it would be 9?
You're close. The 9 would stay as it is, but the ln would do something to this x. So the x would go somewhere.
Would
Anyone
it-
happen to know?
Sorry.
Yeah, go ahead.
Would it multiply with 1 over x to be 9 over x?
Exactly. So whenever the natural log comes up, we just go like this. So let's write down a couple formulas just to go along with this one right here. If natural log comes up, we can say derivative with respect to x of natural log x is just a 1 over x. So that's why on this one, we got 9 divided by x. But that's just one derivative. It's a derivative of a log base e, making a natural log. So also watch out for this one. This one came up on exam 3. The derivative with respect to x of log base b of x. So we have any other base than e, meaning it's not a natural logarithm. This turns into 1 over x, natural log b. That part right there is really easy to miss. So next one, and that's just as tricky in a certain sense. Let's give this one a try. Anyone recall what would happen when you differentiate an exponential like that, 5 power x? I think this is another one of those really kind of tricky formulas as far as calculus derivatives go. So I'd say watch out for this one. I don't want to box it, it makes it look like the answer, but watch out for this one. This one's a tricky formula. And let's write down a couple more formulas to go along with this one right here. Just like on the left column, there's an easier formula. It goes like this. D by dx of e to the x becomes itself, just e to the x. Much like how the derivative of the natural log x is nice, just a 1 over x. No extra things like in the formula down below. But if you're dealing with an exponential that's not to base e, you have to use this formula next. D by dx of base b to the x. It should look a lot like this one in green, except we get b to the x, and natural log b stays up in the numerator. So there's a lot of similarities between the logarithmic formulas and the exponential ones. So back to this problem here, if we differentiate 5 to the power of x, we get the base 5 exponential to the power of x again, multiplied by natural log 5. That takes us to just one last one to take a look at. Any volunteers for the class on what would happen to the derivative of natural log 6?
Would this be 1/6?
It turns out this one is not a 1/6. It's almost like the trickiest part of the problem, essentially. And one thing that kind of helps us to see why this derivative is a little bit weirder is it doesn't follow this process. What's missing is x. If there was an x there, if it was natural log 6x or just natural log x, we would get what we expect on this one. But anyone see what should happen to just a natural log 6 without an x?
Would the 6 maybe come in front of the ln, the natural log?
It would stay in position where it is. That's a good thought, though. On some of these problems, we will be using properties of logarithms as when they come up. I think part D right there looks like a major example, but there's no major property of logarithm that we could really use right here to help us. In the chat, Eli says 0. Yeah, exactly. Good call, Eli. This one comes out to a derivative of 0. Let's put down plus 0 just to emphasize. And there's one and only reason why that's the case. It's because this thing is a constant. And the derivative of any constant will go to a 0, but some constants are really just hard to spot, really. So if you see something like this, another thought you can have is, what really makes it a constant is, if you go y equals natural log 6, this is what you're dealing with. A number or a function that always gives you this same constant value, 1.79. But a second thought you can say is, the derivative of this is the slope of the tangent line, but the slope of the tangent line to this curve is always a 0 slope. So that's why it came out to 0 right here. That means we pretty much did that one. If you had a plus 0 there, there'd be a temptation to erase that or write another step to simplify it down. But you know what? In all honesty, I think it's better to leave the notes just like this, just really highlight this trickiness, that the derivative of that as a constant came out as 0. So we'll leave the notes just like that to emphasize. This one turned into pretty much a huge review question. We had to use a power rule, but we had to do some algebra first. Then there's a logarithmic, an exponential, and a very tricky constant to get through. So that part A was designed to be kind of tough by design, just to review a whole bunch of stuff at once. Taking down to part B, this one's not as bad, but we do need a special differentiation formula. Anyone happen to know which rule we'd be using on part B? Would it be quotient rule, chain rule, product rule, some other rule?
Would it be the chain rule?
It turns out it's not the chain rule on this one. For a real good chain rule, what you're looking for is a function that's inside of another function. And does that come up here in the notes? There'd be a chain rule in example 7. And also, I should pause there. There's a chain rule in this one because x power 4 plus 27 is inside the natural log function. And there's another chain rule right here because 5 times v is inside the exponential function on that one. But it turns out this one right here, this will just be an ordinary product rule for this. So let's give this a try using the product rule formula. Let me see if I can avoid the sun by sitting down now. No, that was a bad idea. A few more minutes. Eventually the sun's going to reach this height, I guess. That'll be my cue that I can use the seat again. So with a good product rule, if you decide to use some color coding or setup, this would be about the way you would analyze it. You would have the first function times the second function, and now g prime of x will be first 18x cubed differentiated, copy e to the x, at 18x cubed copied, and then differentiate e to the x. So that's how this one would be set up, just using the ordinary product rule. On the next line, 18x prime, well, let's see, that's going to be 30, 24, carry the 2, looks like a 54 x squared e to the x. So here we just differentiate that very first term, factor, and copied in e to the x. Then it's plus 18x cubed. The derivative of e to the x is just itself, so we get e to the x here. Then this one's complete. You could do further algebra like factoring or any of those kinds of things, but you're fine just leaving the answer right in that format. Well, that's a product rule down. Next up looks like it's the quotient rule. Any questions on part B? Okay, let's give part C a try next. Let's first indicate what we're doing to it. We're going to hit this one with quotient rule. And chain rule at the same time. So this one's a little bit more challenging. We're combining multiple rules, but we can still set up the quotient rule in the same sort of way. So we have a top function and a bottom function rather than a first factor and a second factor. We'll say next, y prime. Let me fix my color coding first. So next, y prime is going to be equal to something that almost looks like a product rule in the numerator. We take 5b minus 3 prime, copy e to the 5b, use subtraction for the quotient rule, and then go 5b minus 3. Multiply that by e to the 5b prime. Then next thing is go to the denominator, take e to the power 5b, and square it. So that's our setup of the quotient rule. We have just two derivatives we have to maneuver through. This one's not so bad. We'll just get a 5 out of this one. This one's tricky, e to the 5b, because like we said, chain rule comes up, and this is where it comes up. So a decent strategy on this problem is just separate out the difficulty. Y equals e to the power 5b. Let's not call it y. Let's call it just f of v equals e to the power 5b. I forgot our original function is called y. We probably don't want to call this y again. That'd be a conflict of notation. So the chain rule setup that we typically do would look like this. 5b is the easier function to spot as an inner function because it's going inside e to the power v. So this is function 2, inner. This function, the base e exponential, which is written as e to the v typically, is the outer. So now this derivative comes together in this sort of way. F prime of v is, following the chart here, we differentiate the outer function. That's differentiating e power v. It would just give us e to the power, well, we don't put v there, something else is going inside. And then chain rule says immediately multiply by the derivative of that thing going inside this parenthesis. The thing that goes inside here is now the inner function, 5b, and no change on that one. It's just directly copied in. Down below over here, it copies in as 5b. And this has a lot of setup, but in the end of the day, what we're saying is, if you differentiate e to the power 5b, you get itself, e5b, multiplied by the derivative of 5e. There it is being done. We get a 5. I'll put it in front of the function. And that's the whole result. If this was e to the power 7b, we would just get 7 e to the power 7b, for example. So finally, that plugs in over here, and we're just about done with this derivative. Any questions so far to this stage? Running through the chain rule or any of the setup here? Okay, well, let's finalize this one. Here we have one derivative left to go, but derivative of 5b minus 3 is just a 5. So we get a 5 e to the 5b. minus 5b minus 3. Chain rule here gives us 5. E to the 5b. Whole thing is divided by e to the 5b squared. But when you do this kind of exponent raised to an exponent, those things just multiply together. So this is now e to the power 10b if you like. If you left the answer in this format, I'd be okay with that on the final exam, but it really does simplify a little bit further. I'll leave it up to the class. Should we continue with simplifying this one, or would you rather go off to part D? Your choice today.
Can we simplify it just so I can see like the different ways we can answer it?
Yeah, let's go for the simplification. Good call. So one simplification that's going to happen is, notice you have these things everywhere. You could actually cancel them right at this stage. This would cancel, and you would get e to the power of, let's see here, we cancel out e to the power 5e, looks like it'd just be e to the power 5b. So let's try out a different way to visualize it. We'll get 5 e to the power 5b. So I'm factoring that out of the entire first term. That'll leave a 1 right here where the red dot is. This got factored out, so I'm left behind with negative. Let's also distribute that negative inside. Negative 5e plus 3. And sure, we have e to the power 10b, but if we're going to simplify, might not have been a bad idea to actually leave it in that format, e to the power 5e squared. It's a little bit easier to visualize the cancellation. So e power 5e squared still. Now, here's the actual cancellation finally. This cancels 1 power from here, leaving just e to the power 5e. So our end answer could be 5 times. Simplified inside here, we have 4 minus 5e. I'll divide by e to the power 5b. So that would be our final answer. And you know what? Those steps are really actually pretty important. Not as important if there's no context here, but if we were doing something like, say, the first derivative test, if we were optimizing, we really would want to take those steps in order to just find the critical number, for example. We got it, folks. That's a pretty tough derivative because of 2 rules happening on this one. Next up, we'll do a logarithmic one. But any questions at all getting to that end stage? Okay, well, on the real final exam, a property of logarithm sheet is provided, just like on exam 3. So let's work through those properties carefully and see how we can take on this derivative. The first thing that we would want to remark is it's pretty much never a good idea to attack this derivative directly. It's a chain rule with multiple things causing chain rules, not just the natural log, but also e power 10x is a chain rule. Square root 2x minus 11 is a chain rule. There's also a product rule here. There's also a quotient rule. It's one of those problems that just never wants to end. So we can make it simple by just simply going like this. H of t equals natural log. Oh, hang on. I do have a issue right here. This is like the second time that's happened. Sorry about that. If I put x in the function, it should have been an x right here. Let me change that really quick. I think I must have just put these problems together a little too quickly without carefully vetting them. So with a proper x there, we can now begin by saying this is natural log. Oh, hang on. Just for the sake of clarity, we should put x here as well. Now we're ready to begin. So we'll take natural logarithm of the numerator, x, e power 10x, minus the natural log of the denominator, which we'll rewrite as 2x minus 11 to power 1/2. So all we've done here is we split the numerator and denominator into 2 terms across with subtraction. Now, right here, we have a product, so we can maneuver through that. This one's almost simplified, but we can also bring down the exponent. So on our next line, we have, let's focus on this right here. Because it's a x times e to the 10x, it turns into natural log x plus natural log e power 10x. Then finally on this one, 1/2 moves down, and we have minus 1/2 natural log 2x minus 11. And you don't want to celebrate early on these things. This looks like it's simplified, so we're happy with it. Same with this one over here, but this also simplifies. If you think back to the exponential growth problem we did, it's the same kind of cancellation. Those two are gone, and you just get a 10x. So the function will differentiate, will be in the form natural log x plus 10x minus 1/2 natural log 2x minus 11. And I'd say the bigger takeaway with this problem is it's just interesting to know that sometimes this is considered the simplified function. Other times this is the simplified function, but it just totally depends on the context, what you're about to do. If you're differentiating, you never want your function to look like that. You'd want it to be in this format right here. So we come over here and say h prime of x is going to be term by term. First one is 1/x plus, this is linear, so we just get 10 minus 1/2 times. And over here, it's now another chain rule. I didn't mean to say that sounding sad. It's another chain rule. We should be excited about that. So another analysis says this one is the inner function. This ln here is the outer function. So just like before, we go in order, differentiate the outermost function, which means natural log differentiated takes all of its input and just drops it into a denominator. Then through the chain rule, we multiply by the derivative of that input. And 2x minus 11, the inner function, goes in both of those placeholders. So it'll go here and here, which means we're almost done. One more step. We'll work out that derivative and be on our way. So it's a 1/x plus 10. We have a minus from right here. One half times 2x minus 11. I left the numerator here blank because when we crank out this derivative, we get a 2, but we're just going to multiply it into the fraction. It ends up right here, which means there's more cancellations. This problem doesn't want to end. The 1/2 and the 2 here will cancel. And I think we finally got it, folks. Our end answer on this one is 1/x plus 10 minus x over 2x minus 11. If you do this problem directly, you get the same answer, but it's the answer where all of this has had its least common denominator computed and the fractions are all added together. Well, any last questions, folks, on our part D here?
I have a question.
Sorry, say again.
Why is there an x in the numerator for x over 2x minus 11?
Oh, good call on that one. It looks like I just messed up that derivative there. It should have been just a 2.
Okay.
I blamed it on the sun on my eyes, but it wasn't quite in my eyes at that point. Thanks for spotting that one. So this portion right here, yeah, so that should have been just a 2 in the derivative. That means it should have just been a 2 there. And this one would have been a 1. Thanks for spotting that one. Other questions at the moment? Okay, well, coming down the line, looks like we're dealing with local maximum and minimum values. But we're also getting pretty close to the end here. We've got, about 10 more minutes to go. Let's see if we have a problem that we'd rather do first. So this one is about max mins, concavity, inflection points. One down below is about the equation of a particle satisfying the following conditions. We have an optimization, and then something about doing areas. Just because we're at the last day of the class and you've all worked hard making it here today, I did want to give some hints on the final exam. One hint is thinking about asking a question just like this one. where just like example 1 in section 5.1, you'll use a right endpoint rule or a left endpoint rule, not the midpoint rule, and you'd just be using values like off a graph like this one. I'm also looking to ask a question like example H right here. So I feel like for the time we've got, this would be a good one to do next. Does that sound right to folks so far? Okay, let's give this one a try. For the other problems that we're not getting to, I will find the full solutions and get them uploaded. So you could expect to see everything finalized on this document, all the solutions provided when you start studying over the weekend. But let's make this one our last question of the day. Yep, you bet. Glad to help out. So I think this one is kind of tricky because this is the one that came from section 4.6 on antiderivatives. Here's how the steps would go for this one. They gave us an acceleration function. It says find the position function, which means 2 antiderivatives. So here's the step 1 in this process. We go to velocity of t for our very first step. That's the first antiderivative of the acceleration function. And because we're taking antiderivatives, the power 2 we see right here goes up to a power of 3. We then multiply by 1/3. And then pause right here. Visualize if you differentiate that. 3 would come down, cancel as 3/3, and the new power would just be 2, so t squared. So let's do it again. Next term goes minus 4t, but t's power goes up to power 2, so we divide by 2 right here. And one last time, if it's just a constant, we go like this. Plus 6t, we just attach to it the variable t. So we now have a velocity function. We should simplify that a little bit more. It's 1/3 t cubed minus 2t squared plus 6t. With the information provided, we can't actually plug in anything to this one because this is the position at time 0. This is the position at time 1. Neither one of those are telling us velocity. So that means we have to go to step 2. And we're coming down to the position function at this stage. It'll be called S of t. I don't know why S. This comes from the physicists. They like S for displacement or the position function. But it's just another antiderivative of this. So going down the line, let's copy 1/3, give it a little bit of extra space, write down t to now the 4th power, which means we have to multiply by 1/4, effectively dividing by 4. We'll do it again over here, minus 2t cubed now. And hang on, before I get too far, I made one mistake on the velocity function. It's a common mistake that I personally make a lot on these kinds of things when I do antiderivatives. Anyone see what the mistake was?
Was it C?
Yeah, good call on spotting that, absolutely. So don't forget this, plus C. There we go. Without that, we really wouldn't be able to solve for anything using any of these initial values because these both are to help us solve for these constants that we get. So sorry for that omission. That is not a good step to forget. So don't forget that advice there. Now let's continue on with the antiderivative. So we were at negative 2t cubed. We bumped the power up to 3, which means we also have to divide by 3 right here. Then one more time, plus 6t, well, 2 more. New power is power 2, so we divide by 2 here. Plus, this one's a new constant, so we attach a t to it, c times t. And then another arbitrary constant of integration, we can call it a new letter d. Same comment, don't forget the second constant of integration. Let's simplify this a little bit more before we finalize and start solving for the constants. So at the moment we have the position at time t is 1/12 t power 4 minus 2/3 t cubed plus 3t squared plus c times t plus d. So nothing major happened on this step except a couple small simplifications. Now we come back up here, start using the initial conditions and solving for the constants. We'll start with this one. It's just a little bit easier to use because we're plugging in 0 for t. So s of 0 equals 0 would imply on the left-hand side, we're plugging in 0 for every value of t that occurs. So that would mean 0 plus d equals 0. So the 0 plus d is the result of zeroing out all these terms. And then finally, here's the plus d. But what it tells us is d is 0. So we could just ignore that term entirely. We now have position function at time t is a 12 t power 4 minus 2/3 t cubed plus 3t squared plus c times t. So we're left off the constant d because it's zeroed out. Next one, looks like it might take a little bit more algebra, is this one. The position at time 1 is 20 meters or feet away from the starting position. So let's work this one out. S of 1 equals 20. That then implies we're plugging 1 everywhere t occurs here. So we would get a 12. T power 1 to the power 4 is just a 1. So again, negative 2/3 plus 3. We're plugging a 1 inside here, so this just turns into plus the constant c. The right-hand side is equal to 20 now. And looks like we have some fraction arithmetic, but don't forget you do have a calculator available to you on the final exam. Let's just treat ourselves to a fast computation. Let's take 20 minus 3 plus 2/3 minus a 12. Let me double check the arithmetic on that. Minus a third plus 2/3 minus a 12. Looks like we've got it. Let's trick ourselves in either giving a fraction if you like, or if you gave me the decimal number of a problem like this, I'm totally fine with that as well. Let's go with the decimal. 17.58 looks like we're repeating. So C equals 17.583 repeating. And the last thing we can now say is, therefore, the position at time t is come back over here and just change this one thing. So it's a 12 t power 4 minus 2/3 t cubed plus 3t squared plus 17.583 bar times t. So we did it, folks. This is a kind of problem that you can expect on the real final exam on just doing the antiderivatives. Any questions at all getting through this process?
I have a question just about this study guide in general.
Yeah,
Would you say this is going to be more comparable to the final exam, or should we refer more to the long one at the end?
that's a good question. In all honesty, the motivation behind making this one was just to make this one really, really short so we can go through most of the questions during the exam time. I would say the problems here are going to be similar to the problems here as far as the final exam goes. Looking
Okay.
at either document would be really helpful. So think of this as the abridged version. And this one you'd want to go and target specific sections, not necessarily doing every single problem. Same with
Okay.
the version down below. Other questions at the moment? Okay, well, it looks like a natural stopping point for us. No matter how fast we go, we can't solve this one in 1 minute. But like I mentioned, I will upload the results, the solutions to each one of these. But have a great afternoon, folks. If you do have more questions, I have office hours today, office hours tomorrow at this usual time. Otherwise, have a great study session. And if questions come up, please don't hesitate to email. I'll be very happy to help out. Take care, folks, and we'll talk to you all later.
Can I ask you a question? It's not very long. I don't know if I should wait for office hours. Um, but for questions like example 9, are we basically doing, I forget what section it was, where we're given a function and we find the maximum.
Pretty much, yeah.
First
This is
derivative
very
test?
similar to section 4.2, first derivative test.
Okay.
So
And
yeah,
then, so the only difference is making that like kind of number line and finding out where it's positive and negative, right?
exactly. That's pretty much exactly what you'd be doing on this one.
Okay, perfect. Thank you.
Yep, absolutely.